Hello everyone and welcome to the second hour of nuclear physics and radioactivity, and in this hour we are going to focus on radioactivity. So without wasting time, let's start. The first thing we are going to talk here is about nuclear radiations. If you have got a substance whose nucleus is unstable, then we find that it gives out certain type of radiations. Now these radiations are different because we have done different type of test on them. For example, let's say here you have got a material whose nucleus is unstable. We know that different type of radiations come out of it because if we make the radiation pass between two plates of negative and positive charge, we find that these radiations deflect towards one of them. Now it is obvious that if you have got a plate of negative charge and a plate of positive charge, then an electric field will exist in the region between the plate. And this electric field will be from positive plate towards the negative plate. Now if let's say a particular type of radiation coming out of it move towards the negative plate, it means that this particular radiation have a positive charge because it has been attracted by negative plate. If a particular type of radiation coming out of this nuclear material gets attracted towards the positive plate, it means that this particular radiation must have negative charge because it has been attracted towards the positive plate. And if the radiation coming out goes undeflected, it means that that radiation is uncharged, no charge, zero charge, neutral. So it was observed that when we make the radiations pass, one of the type of radiation bend towards the negative plate. This must be positively charged. We call them alpha rays. And today we all know that what is alpha rays? Alpha rays are made up of nothing but alpha particles, and alpha particles are nothing but helium nuclei. So they have got 2 proton and 2 neutron. So the charge is plus 2e and the mass is nearly 4 AMU. Then we found another type of radiations coming out of this nuclear substance because these radiations move towards the positive plate. If the radiations bend towards the positive plate, this means that these radiations must be negatively charged. We call these rays as beta rays. We know that beta rays constitute of nothing but electrons. As of today, we talk about two types of beta rays. We say that beta plus rays and beta minus rays. Beta plus rays are made up of positrons, while beta minus rays are made up of electrons. And then we have got another type of rays which are undeflected by the electric field present in between the region, and we call these as gamma rays. And today we know that gamma rays are made up of nothing but highly energetic photons. In the entire electromagnetic spectrum, the most energetic photons belong to the part of the gamma rays. In the entire electromagnetic spectrum, the most energetic photons are the one who make the gamma rays. So gamma rays are neutral. They are nothing but electromagnetic radiations of high energy. Exactly same result were obtained when these radiations were subjected to magnetic field. So if rather than making the radiations pass through electric field, if we make them pass through the magnetic field, we also found that one type deflected towards one side, another type deflected to another side, and one type is not at all deflected. It means that this gamma rays have to be electrically neutral. Now, do take this as a word of caution. Every time they just say beta rays, it means that it is beta minus rays made up of electron. No doubt, observing beta plus radiation is rare. Why? I will explain a little bit later. Now I am going to tell you 2 points here that will confuse you more, but believe me, I will explain them as I will explain different type of radiation. So the first thing, no radioactive substance emits both alpha and beta particles simultaneously. If I have just said beta, it means that I am talking about beta minus. So you do not find that from a nucleus both alpha particle and beta particle are coming out simultaneously. This doesn't happen. Why? We'll explain when I individually explain alpha radiation and beta minus radiation. The extension of this point is also gamma rays are emitted after the emission of alpha or beta particles. So sir, you are saying that alpha and gamma are not emitted simultaneously. No. If alpha particle is emitted by the nucleus, after some time the gamma radiation is emitted. Why? For sure, I will explain when I deal with them individually. Second point, bachcho. Beta particles are not orbital electrons. Beta particles are nothing but electrons, but they are not orbital electrons. They come from the nucleus. So beta particles are emitted from the nucleus. So sir, you are saying that electrons are emitted from the nucleus. Yes. But sir, there are no electrons in the nucleus. Yes. If one of the neutron present in the nucleus convert into proton plus electron plus something else, then this electron is not allowed to live inside the nucleus. Who lives inside the nucleus? Nucleons. Who are nucleons? Neutron and protons. So once this electron has been created inside the nucleus, it comes out of the nucleus. And these electrons coming out of the nucleus are called beta particles. So beta particles are not orbital electrons. Those are not the electrons moving around the nucleus. They come from the nucleus. The neutron in the nucleus decays into proton and an electron. This electron is emitted out of the nucleus in the form of beta rays. So I think that second point you might have understood. First point you might have doubt. Have faith that this will be cleared when I talk about each type of radiation individually. So let's now start talking about each type of radiation individually, and the first type of radiation I'm going to talk about is called alpha decay. Alpha decay means that when an alpha particle comes out of the nucleus. What is an alpha particle? Nothing. Helium nuclei. 2 proton and 2 neutron clubbed together, they form an alpha particle. So when an unstable nuclei emits an alpha particle to attain stability, that's called alpha decay. So if you have a nucleus whose atomic number is Z, it means that the number of protons are Z, and mass number is A, it means that number of nucleons are A. If this particular nucleus gives out an alpha particle, you will say that now the number of protons will be 2 less, because alpha particle is nothing but 2 proton plus 2 neutron. Since now the number of protons will be 2 less, the new atomic number will be Z minus 2. And since 2 proton and 2 neutron have came out, how many nucleons have came out of the nucleus? You will say, sir, 4 nucleons have came out. That's why the mass number reduces by 4. So you get a new nucleus. This is called daughter nucleus, which has got 2 less protons and 4 less nucleons. Hence, the atomic number is Z minus 2 and the atomic mass is A minus 4. 4 less than the original. Plus, you get an alpha particle, which has got 2 proton and 4 nucleons. And after the emission of alpha particle, you get a gamma ray coming out of it. Now, bachcho, you need to understand that whenever a nucleus undergo alpha decay, the mass number reduces by 4. The atomic number reduces by 2. So if from a particular nucleus, let's say they say 3 alpha particles are coming out. So you will say for every single alpha particle coming out, the mass number reduces by 4. So if 3 alpha particles are coming out, then the mass number will reduce by 12 and the new mass number will be A minus 12, given that the original mass number is A. And if 3 alpha particles are coming out, then the atomic number will decrease by 6, because for every single alpha particle coming out, the atomic number reduces by 2. So if 3 alpha particle comes out, then the atomic number will reduce by 6. So if the original atomic number was Z, the new atomic number will be Z minus 6. So that's the basic idea. Now what I'm going to tell is important. N by Z ratio increases when a nucleus undergo alpha decay. So what is the meaning of this N by Z ratio increases? Beta, first of all, what is the meaning of N by Z ratio? The number of neutrons upon the number of protons. That is the meaning of N by Z ratio. For small nuclei, N by Z ratio is found to be equal to 1 for a stable nuclei. But for heavier nuclei, the number of neutrons should be more than the number of protons. Hence, N by Z comes out to be more than 1. Now let's take an example. Let's say you have got a particular nucleus in which you have got 12 neutrons and 10 protons. 12 neutrons and 10 protons. What is the n by z ratio right now? So you will say, sir, the n by z ratio right now is 12 by 10, that is 1.2. If an alpha particle comes out of this particular nucleus, then after the emission of alpha particle, 2 proton will go out and 2 neutron will go out. So the new number of neutrons will be 10 and the new number of proton will be 2 less than the original, so that will be 8. So the new n by z ratio will be 10 by 8 and 10 by 8 is 1.25. I have taken this example to make you understand that whenever a heavy nucleus undergo alpha decay, then the n by z ratio increases. The n by z ratio, which was originally 1.2, now becomes 1.25, greater than the original. So I have taken some numbers to make you understand this, but you need to remember that with an alpha decay, the n by z ratio increases. And this is the key why you can't have alpha decay and beta minus decay simultaneously. So you need to keep this point in mind to understand that why they can't happen together. Now we are going to talk about beta decay. There are two types of beta decay. There is beta plus decay, there is beta minus decay. When we say beta plus decay, it means that positron comes out of the nucleus. And when we say beta minus decay, it means that electron comes out of the nucleus. Beta minus decay are more commonly observed type of beta decay. That's why if somebody only mentions beta decay, it goes without saying that they are talking about beta minus decay. I will even explain why beta minus decay are more commonly observed compared to beta plus decay. Now bachcho, what is the meaning of beta minus decay? When a beta minus particle, an electron comes out of the nucleus, that is said to be beta minus decay. How does an electron comes out of the nucleus? One of the neutron present in the nucleus converts into a proton plus an electron, and that electron leaves the nucleus and comes out of it, and that is recorded as beta minus decay. So let's say there is one of the neutron out of the many neutron present inside the nucleus that converts into a proton and an electron plus few more particles. We will talk about them later. Do notice that the charge on a neutron is 0 and the mass on neutron is 1 AMU. It converts into a proton which has got charge of plus 1 E and mass of 1 AMU, and an electron which has got charge of minus 1 E and there is no mass. Means we know that electron has got mass, but the mass of electron is nearly 1/1837 times the mass of proton. So when we are writing the mass of electron in AMU, it is nearly equal to 0. So that's why a 0 written here. After the emission of electron from the nucleus, there is a successive emission of high energy photon that is called gamma radiation. Why this takes place? We'll explain when I talk about gamma decay. But first, we need to talk about this another particle. Sir, what is this? This particle is called antineutrino. Antineutrino. Do remember that every time a neutron dies, an antineutrino is born. Why have we placed this particular antineutrino here? What is its property? What is its nature? We are not going to talk about it. I'm going to tell you only one thing, that it was first placed here to balance a particular thing called spin. If we do not place antineutrino, then the spin on the left hand side of equation is not equal to the spin on the right hand side of equation. So as to balance the spin, Wolfgang Pauli, the same guy who gave the Pauli's exclusion principle, proposed that there has to be one more type of particle, and he called it antineutrino for this particular case. And it was later discovered after many years that yes, it exists. So do remember that every time a neutron dies, an antineutrino is born. It is placed here to balance the spin on both the side of equation. Now bachcho, if we talk the same type of decay for a nucleus, if a particular nucleus undergoes beta minus decay, then what happens? Let's say there is a particular nucleus having symbol X, having number of protons Z, and having a mass number A. If this particular nucleus undergoes beta minus decay, it means that one of the neutron present inside the nucleus converts into proton plus electron, and then the electron comes out of the nucleus. It means that the number of proton in the nucleus increases by 1. So the new atomic number will be Z plus 1. Can you think and tell what happens to the mass number, which is the number of nucleons? The number of nucleons in the nucleus remains the same. One of the neutron present inside the nucleus has converted into one of the proton. But the total count of nucleon, which is the sum of proton plus neutron, remains the same. Hence, the mass number remains the same. So when a nucleus undergoes beta minus decay, we say that, let's say original nucleus is ZXA. The new nucleus, let's say, has a symbol Y because the number of proton has changed. So the type of atom has changed. So its symbol must change. So the new nucleus will have number of protons Z plus 1. The mass number remains the same because the number of nucleons remains the same. Only one of the neutron has converted into one of the proton. Plus an electron comes out of the nucleus. Plus an antineutrino comes out of the nucleus, and there is a successive emission of an high energy photon. Do understand that every time a nucleus undergoes beta minus decay, the mass number of the nucleus remains the same as the number of nucleons remains the same. The atomic number increases by 1. So when the nucleus undergoes beta minus decay, for every single beta minus decay, the atomic number increases by 1. So if a particular nucleus undergoes 5 beta decay, they just say 5 beta decay, do not tell you beta plus or beta minus. You have to assume that they're talking about beta minus. So you will say, sir, for every single beta minus decay, the mass number remains unchanged. So if even 5 beta particles are coming out, the mass number will remain the same. If it was originally A, it will remain A. But for every single beta minus decay, the atomic number increases by 1. So for 5 beta minus decays, the atomic number will increase by 5. So if the original atomic number was Z, the new atomic number will be Z plus 5. Now comes the important part, which explains that why alpha decay and beta decay, which is beta minus decay, can't take place simultaneously. For alpha decay, we learned that every time a nucleus undergoes alpha decay, N by Z ratio increases. But when a nucleus undergoes beta minus decay, you should understand that N by Z ratio will decrease. Why? Sir, N by Z ratio is what? The number of neutrons upon the number of protons. When the nucleus undergoes beta minus decay, one of the neutron inside the nucleus is converting into a proton. So the number of neutrons are decreasing, the number of protons are increasing. So the N by Z ratio is decreasing. Now, if you have an unstable nuclei, either to attain stability, it should increase the N by Z ratio, or it should decrease the N by Z ratio. If to attain stability, it has to decrease the N by Z ratio, then you are going to observe beta decay. If to attain stability, it should increase the N by Z ratio, then you will observe alpha decay. You can't observe both the decays simultaneously because their purposes are different. One of them increases the N by Z ratio while the other one decreases the N by Z ratio. That's why you don't find alpha decay and beta minus decay taking place simultaneously. Now, bachcho, moving on to the next type of decay, and I know that you know it, we are going to talk about beta plus decay. Beta plus decay means a positron is coming out of the nucleus. What is a positron? You have to think of positron as a small charged particles having mass same as that of mass of electron and having charge same as that of charge on proton. So for a positron, you will say that the charge on positron is nothing but same as the charge on proton, that is plus 1e. Plus 1 times 1.6 into 10 raised to the power of minus 19 coulomb. And when you think about mass of positron, the mass of positron is equals to 1 by 1837 times the mass of proton. Considerably very small mass compared to that of proton, the mass equal to that of electron. Positron is the true antiparticle of electron. So when we say that beta plus decay takes place, it means that when a positron comes out of the nucleus. Now, sir, how does a positron comes out of the nucleus? How is a positron formed? When one of the proton present into the nucleus converts into a neutron, it gives out a positron. So one of the proton present in the nucleus converts into a neutron plus a positron, plus this time one more type of particle has been named, and this particle is called neutrino. Every time a neutron dies, antineutrino is born. Every time a neutron gets birth, a neutrino is born with it. And after the emission of positron, we get a successive emission of high energy photon, that is called gamma rays. When I saw this particular equation for the first time in my life, I was so perplexed. And I was perplexed because of one simple thing, and I knew it from childhood, that neutron has got more mass than proton. Then how is this possible that a proton gives out a neutron? So less mass gives out more mass. Now here comes the understanding of Einstein's mass energy correlation. Einstein told us that mass equals to energy upon c square. Yes. If you talk about an isolated proton, and you talk about an isolated neutron, then no doubt isolated neutron has got more mass than isolated proton. But if somehow you can increase the energy associated with the proton, put the proton in an unstable state. In unstable state, energy is more. So if you put the proton in an unstable state, its energy increases. If the energy increases, so does the mass. So do understand that an isolated proton has got lesser mass than an isolated neutron. So an isolated proton cannot convert into a neutron plus positron. Only a highly energetic, means more mass, only a highly energetic or only a highly unstable proton can undergo beta plus decay, because only a highly unstable proton will have such huge mass to give out the mass of a neutron plus a positron. So do remember these lines of mine. No ordinary proton undergoes beta plus decay. Only highly energetic proton, only highly unstable proton undergoes beta plus decay, because only highly unstable or only highly energetic proton has got that mass to give out the mass of a neutron. Okay, I hope this point is clear. So that's why beta plus decays are less commonly observed compared to beta minus decays, because for the observation of beta plus decay, the proton should have more mass. To have more mass, it should have more energy. Now beta, when we talk about beta plus decay in the terms of a nucleus, rather than talking about individually what is actually happening inside the nucleus, let's say you have a nucleus of symbol X, atomic number Z, and mass number A. If this particular nucleus undergoes beta plus decay, it means that one of the proton inside the nucleus is converting into a neutron plus a positron plus a neutrino. So if one of the proton converts into a neutron, tell me what will happen to the atomic number once the nucleus has undergone beta plus decay. So sir, one of the proton has converted into one of the neutrons, so the number of proton will decrease by 1. So the new number of proton will be Z minus 1. So the new atomic number will be Z minus 1. And what about the mass number? Sir, one of the proton inside the nucleus, no ordinary proton, highly energetic proton. If one of the proton inside the nucleus converts into a neutron, sir, no doubt the number of proton decreases by 1, the number of neutron increases by 1, but the number of nucleons, the sum of the number of proton and neutron remains the same. So the mass number will remain the same. So if a nucleus undergoes beta plus decay, the new number of protons will be 1 less. So the atomic number will be Z minus 1. The mass number remains the same. You will get a positron coming out of the nucleus as well as a neutrino coming out of the nucleus. And after the emission of positron, you will get a highly energetic photon coming out of the nucleus, and that's called gamma rays. Do you understand? When a nucleus undergoes beta plus decay, the mass number remains the same. So both in beta minus decay as well as in beta plus decay, the mass number remains the same. In alpha decay, the mass number reduces by 4. Next thing beta, in beta plus decay, the atomic number decreases by 1. Atomic number decreases by 1. So if a particular nucleus undergoes, let's say, 4 beta plus decay, though beta plus decay are not very commonly observed, but let's say hypothetically, a particular nucleus undergoes 4 beta plus decay. So the mass number will still remain the same, because for every successive beta plus decay, the mass number won't change. So mass number still be A if it was originally A. What about the atomic number? For every beta plus decay, the atomic number reduces by 1. So if you have got 4 beta plus particle coming out of the nucleus, 4 positron came out of the nucleus, then the atomic number will reduce by 4. So the new atomic number will be Z minus 4, given that it was originally Z. Next thing bachcho, when a nucleus undergoes beta plus decay, what happens to N by Z ratio? So it's obvious. The nucleus is undergoing beta plus decay, so one of the proton is getting converted into neutron. So the number of neutron increases, the number of proton decreases, the numerator is increasing, the denominator is decreasing. So the N by Z ratio is increasing. So when a nucleus undergoes beta plus decay, N by Z ratio increases. And the important point for beta plus decay, an isolated proton does not show beta plus decay. No ordinary proton can show beta plus decay. Only highly energetic proton, only highly unstable proton shows us beta plus decay. So now let's talk about next decay, that is gamma decay. Let me ask you a simple question. Think of the helium nucleus. Helium nucleus has got 2 proton and 2 neutron. And think of 2 cases, case 1, case 2. Case 1, 2 protons and 2 neutrons are arranged like this. Case 2, 2 protons and 2 neutrons are arranged like this. I ask you to guess a simple question. Will both of these configuration or the arrangement of nucleons inside the nucleus will have same energy or different energy? And does your heart tells you that one of them will be more stable than the other? I know that your heart is telling you that this one will be more stable. And why? Because you can see that here it's more kind of, symmetrical structure. So this will have different energy from this one. Now this was the example of a helium nucleus which has got very less number of nucleons. If you leave apart hydrogen, the smallest of all, these are the minimum number of nucleons you can deal with, 4. Bigger nucleus have got huge number of nucleons. So let's say 235 nucleons, 238 nucleons. And there are many different possibility of arrangement of these nucleons. Now do understand, sometimes a nucleus transitions from less stable configuration to a more stable configuration. Or you can think, sometimes a nucleus transition from high energy configuration to a low energy configuration. Low energy configurations are more stable configurations. So if a heavy nucleus has got huge number of nucleons, there can be many different possibility of arrangement of nucleons within the nucleus, and all of them won't have same energy. Some of the cases will have more energy, some of the cases will have less energy. More energy means less stability, less energy means more stability. So when the nucleus transition from lesser stable state, more energetic state, to a more stable state, lesser energetic state, it gives out a high energy photon. And that high energy photon is nothing but gamma photon, and this type of decay is called gamma decay. So sometimes a nucleus transitions from less stable configuration to a more stable configuration, giving out a high energy gamma photon, and this is called gamma decay. So in a gamma decay, what comes out of the nucleus? So nothing but gamma rays. What is the charge on gamma rays? So no charge. What is the mass of gamma rays? So there is some moving mass, we can find it, we have learned it, but technically you can take it as 0. So we can say that an unstable nucleus converts into a stable nucleus by giving out a high energy photon, which are called gamma rays. Now do understand that since the number of protons haven't changed, the symbol will be same, it represents the same nucleus, and the mass number also remains same. Personally, I like gamma decay the most because here nothing changes. So to understand, in case of gamma decay, mass number and atomic number remains the same. What happens to N by Z ratio? So that also remains the same. Nothing has changed here. Okay. So you need to understand one thing. In only alpha decay of the cases we have learned till now, the mass number changes. In all the other three type of decays we have learned, the mass number remains the same. Now let's talk about something called K capture. K capture. What is the meaning of K capture? The name itself says visualize an atom. We know that in the center there is a nucleus. And if we think of the simple model, not the probabilistic model, where the electrons are revolving in orbits around the centralized nucleus. In the first orbit we have got 2 electrons, in the second orbit we have got 8 electrons. I know that you have learned the 2n square formula, and you know how many number of electrons are there in each orbit. Now let's say this particular atom is no ordinary atom. This particular atom is such an atom which has got huge number of proton in its nucleus. So if we have a nucleus of high atomic number which has got huge number of protons present in the nucleus, then for such a nucleus it will have huge amount of positive charge. And when the nucleus will have huge amount of positive charge, the electrostatic force of attraction on the innermost electrons will be huge. So if we have a nucleus of high atomic number, the force on the innermost K shell electrons is large. And if the force of attraction on these innermost K shell or L shell electrons is large, sometimes it is found that they end up jumping into the nucleus. But when the electron gets captured, hence the name K capture, getting the electron captured from the innermost orbit, K capture. So if the electron jumps into the nucleus, electron is not allowed to live inside the nucleus. Then what happens? The electron, if it falls into the nucleus, combines with a proton to produce a neutron. So you will say that once this innermost shell's electron has been captured, this electron has to combine with a proton present inside the nucleus to convert into a neutron. And this phenomenon is called K capture. So you will say that a proton plus electron, the electron has been captured from the K shell. This electron has came from outside the nucleus. And this proton plus electron converts into a neutron. Every time a neutron is born, a neutrino is born. And definitely this process has taken place. To attain stability, a high energy photon is radiated out, and this is called gamma photon. So you will say that a proton plus electron converts into a neutron plus a neutrino, and a gamma photon comes out of the nucleus. If we talk in terms of atom, if the atom has the symbol X, the number of protons Z, and the atomic mass A, then once the electron has fallen, one of the proton converts into neutron. So the number of nucleons remains the same, so the mass number remains the same. But now since one of the proton has converted into neutron, the atomic number reduces by 1. So we say ZXA converts into Z minus 1. Since the number of proton has changed, so will the symbol. The mass number remains the same. Plus you get a neutrino coming out of the nucleus plus a high energy radiation. So whatever we have learned till now in decays, better do understand only in alpha decay the mass number changes, and for every alpha decay the mass number reduces by 4 and atomic number reduces by 2. Now better understand that mass number remains the same, atomic number decreases by 1 when a particular atom shows K capture. Now let's talk about the type of conservation principles that can be used in nuclear reactions. The first type we are going to talk about is conservation of mass number and charge number. Beta, first of all, observe that I am talking about mass number. I am not saying mass. In a nuclear reaction, mass is not conserved. Mass converts into energy, energy converts into mass. We have learned the Einstein's mass energy equivalence equation. What remains conserved is mass number. That is the total number of nucleons. And definitely the charge remains conserved. So let's think of a nuclear reaction in which helium plus nitrogen converts into oxygen plus hydrogen. If we think of the mass number before the reaction and after the reaction, Before the reaction, you will say that the total mass number of reactant is 4 plus 14. So the mass number is 18. And after the reaction, the mass number is 17 plus 1. So after the reaction, the mass number is still 18. So the mass number remains conserved. Mass is not at all conserved. Now let's talk about charge number. So you will say that the total charge before the reaction is 2 plus 7, that is 9. And the total charge after the reaction is 8 plus 1, that is also 9. So the charge remains conserved and mass number remains conserved. We can even apply the principle of conservation of linear and angular momentum. So in nuclear reactions, we can conserve momentum, both linear as well as angular. So linear momentum and angular momentum of particles before the reaction is equal to linear momentum and angular momentum of the particles after the reaction, given that no external force or no external torque is acting on the system of particles. Then we need to talk about another conservation principle that is valid in nuclear reaction, and that is the conservation of energy. Here, do understand that we even consider mass as a type of energy. With a mass m, the energy associated is mc square. So total energy, including the energy term due to mass, before the reaction is equal to the total energy after the reaction, including the term of mass definitely. Term Q is added to balance the total energy of the reaction. In the last hour, we have talked about Q value. Q value means the energy released during the nuclear reaction. If the energy is released, Q is positive. If the energy is absorbed, then Q comes out to be negative. Keep this small thing in mind. Now let's talk about the most important thing of this hour, and that is the law of radioactive disintegration. Let's say we have got a radioactive substance and we have got n number of radioactive nuclei. So we know that these radioactive nuclei disintegrate over the period of time. If I ask you what will be the sign of dN by dt, you will say, sir, dN by dt. What does dN by dt represent? The rate of change of number of active nuclei with respect to time. As the radioactive nuclei will disintegrate, the number of radioactive nuclei will decrease. If the number of radioactive nuclei will decrease, then you can say that dN by dt must be negative. So as to keep the terms in the equation positive, we place a minus sign with dN by dt. Now minus dN by dt is negative of negative, and that becomes positive. So we say that in a radioactive disintegration, minus dN by dt, which represents the number of disintegration per second, is directly proportional to the number of active nuclei. The greater the number of active nuclei are there in a sample, the greater is the rate of disintegration. As the disintegrations will take place, the number of radioactive nuclei will decrease, and so will the rate of disintegration. And every time in this world a physicist has found a proportionality, what do? They add up a proportionality constant. So we write the law of radioactive disintegration as minus dN by dt, minus sign to make the left hand side of equation positive, equals to lambda n. So the law of radioactive disintegration goes like dN by dt equals to minus lambda n, or you can write it as minus dN by dt equals to lambda n. So this is the law. Here understand that lambda depends only on the nature of substance. The greater the radioactivity of the substance, the more unstable the nuclei are, the higher the value of lambda, because for same number of active nuclei, you will get more number of disintegrations per second. It is independent of the time. It means that if you have a particular sample of radioactive substance right now and you have got n number of radioactive nuclei, after some time, let's say you have got n dash number of radioactive nuclei. As the sample keeps on decaying, the number of radioactive nuclei at a later stage n dash will be less than the initial number of radioactive nuclei for sure. But the value of lambda do not change with time. lambda remains constant, and physical or chemical changes. So lambda is independent of time, physical changes as well as chemical changes. From this particular equation, on solving, we can get the equation that the number of active nuclei at any time t equals to initial number of active nuclei e raised to power of minus lambda t. So how do we get this? It's quite easy. Look at this equation. You can write minus dn by n equals to lambda dt. Integrated both the side. Integration of dn by n gives you minus ln n. Take the initial number of active nuclei as n0 and the number of active nuclei at any time t as n equals to lambda times integration of dt gives you t, take the initial time as 0 and final as t. Substituting upper limit minus lower limit, you will get minus ln n minus ln n0 equals to lambda t. So this gives you minus ln n by n0 equals to lambda t. Or you can write ln n by n0 equals to minus lambda t. Or you can write n by n0 equals to e raised to power of minus lambda t. Or the number of active nuclei at any time t equals to initial number of active nuclei into e raised to power of minus lambda t. That is the equation of radioactive decay. So if you think of the graph of number of active nuclei versus time, the number of active nuclei keeps on decreasing with time and the graph is an exponential graph like this. So at time equals to 0, the number of active nuclei are n0, and as the time keeps on increasing, the number of active nuclei keeps on decreasing. How much time it will take for %% of the radioactive nuclei to disintegrate? It will take infinite time. Now, bachcho, here we need to understand one thing which is really important, and that is the law is based on statistical model and works on a large sample space. What is the meaning of it? You can't apply this law on 10 nuclei, 20 nuclei, 30 nuclei. The number of active nuclei should be very large. It should be of the order of Avogadro 6.023 into 10 raised to the power of 23. You need to talk about many nuclei to apply this particular law. This law doesn't work on 50, 60, 70 nuclei. This law doesn't work on a small sample space. The number of active nuclei you should have should be very large. Next, bachcho, the radioactive material decays using first order kinetics. Even while learning chemistry, you must have found this type of equation for the reactants. The reactant here decays following the first order kinetics. Notice that dn by dt directly proportional to n raised to the power of 1. So the radioactive material decays using first order kinetics, and if you have been with me for so many hours, I must have said this at some point in time that all first order decays have a beauty of their own, and that beauty is that equal percentage change takes place in equal interval of time. Equal percentage change takes place in equal interval of time every time there is a first order decay. What is the meaning of this statement? To understand it, let's take some example. Let's say at time equals to 0, the number of active nuclei you have is n0. And you find that at a later time, at time equals to, let's say, 1 minute, the number of active nuclei have reduced from n0 and became 0.9 n0. So you can think that if initially the number of active nuclei were n0, then in a time frame of 1 minute only, n0 by 10 have decayed, 9 n0 by 10 have survived. That's why I have written that the number of active nuclei after 1 minute is 0.9 n0. Now, whenever a particular equation follows first order kinetics, there is equal percentage change in equal interval of time. So, if the quantity has decreased from n0 to 0.9 n0, it means that in a time frame of 1 minute, 1/10 has decayed and 9/10 has survived. 1/10 has decayed and 9/10 has survived. This means that after 1 more minute, that is at time equals to 2 minutes, 1/10 of this remaining will decay and 9/10 of this remaining will survive. So if at time equals to 1 minute, you have got 0.9 N naught. In the next 1 minute time frame, 1/10 of this will decay. And what is 1/10 of 0.9 N naught? So sir, 1/10 of 0.9 N naught is 0.9 N naught divided by 10. That is equals to 0.09 N naught. So in the next 1 minute time frame, out of 0.9 N naught, 0.09 N naught will decay. So how much will be left? So sir, out of 0.9 N naught, 0.09 N naught will decay. So what will survive after 1 more minute will be 0.9 N naught minus 0.09 N naught. That will give you 0.81 N naught. Do the maths. There is a smarter way to understand this. The smarter way starts now, and listen to it carefully. You can say that after 1 minute, yes, the number of active nuclei becomes 0.9 times. Then after 1 more minute, the number of active nuclei will be 0.9 times of the remaining, and 0.9 times of 0.9 N naught gives you 0.81 N naught. Yes sir, that can be thought of. Let's take one more example to understand. Let's say at time equals to 0, you had N naught number of active nuclei. At time equals to 2 hours, now you have got 3 N naught by 4 number of active nuclei. So you can say that in 2 hours, 1/4 has decayed. And in 2 hour time frame, 3/4 of the original have survived. If 1/4 has decayed and 3/4 have survived, then after 2 more hours, that is from the beginning at time equals to 4 hours, 1/4 of remaining will decay and 3/4 of remaining will survive. And what will be 3/4 of this remaining? So 3/4 of this remaining will be 3 by 4 times 3 N naught by 4. So that will be equals to 9 N naught by 16. At time equals to 4 hours, the number of active nuclei has to be 9 N naught by 16. If you understand this, solving questions based on radioactivity will be way easier. So let's practice this more with more number of examples. Let's see next example. Let's say at time equals to 0, you have got N naught number of active nuclei. At time equals to 4 hours, you have got N naught by 6 number of active nuclei. It means that in a 4 hour time frame, 5/6 of the original has decayed and only 1/6 of the original have survived. So after 4 more hours, that is from the beginning at time equals to 8 hours, the number of active nuclei will be 1/6 of the remaining. Think of it this way. In the first 4 hours, 1/6 of original survived. So in the next 4 hours, 1/6 of remaining will survive, and 1/6 of N naught by 6 gives you N naught by 36. So at time equals to 8 hours, the number of active nuclei will be N naught by 36. Let's practice more. Let's take this example. At time equals to 0, let's say you have got N naught number of active nuclei. At time equals to 3 year, let's say these number of active nuclei reduces from N naught and become 2 N naught by 3. So you will say, sir, in a time frame of 3 years, yeah, the number of active nuclei becomes 2/3. So in another 3 years, that is 6 years from the beginning, after 6 years, the number of active nuclei will be 2/3 of this. Because in another 3 years, 2/3 of this will survive and 1/3 of this will decay. So at time equals to 6 years, the number of active nuclei will be 2 by 3 times 2 N naught by 3, and that gives you 4 N naught by 9. If I ask you further, then tell me at time equals to 9 years, how many number of active nuclei we will have? You will say, sir, again, starting from here, in the next 3 years, 2/3 of this will remain and 1/3 of this will decay. So 2/3 of 4 N naught by 9 will give you nothing but 8 N naught by 27. So at time equals to 9 years, the number of active nuclei will be 8 N naught by 27. Let's take one more example. Let's say at time equals to 0, you have N naught number of active nuclei. At time equals to 2 days, in 2 days, the number of active nuclei become N naught by root 2. Then tell me at time equals to 4 days, how many number of active nuclei you will have. So you will say, sir, in a 2-day time frame, yeah, the number of active nuclei become 1 by root 2 time. So in the next 2 days, it will become 1 by root 2 times of remaining. And 1 by root 2 times of n naught by root 2 will give you n naught by 2. So the number of active nuclei becomes half. Now, the time in which the number of active nuclei becomes half, that is called half-life. So for this particular sample, you will say that the half-life is nothing but 4 days. If they ask you what will be the number of active nuclei at time equals to 6 days, you will say, sir, it's easy. We know that in every time frame of 2 days, the number of active nuclei become 1 by root 2 times of from where you begin. So in the next 2 days, that is from 4 days to 6 days, the number of active nuclei will change from n naught by 2 and become n naught by 2 times 1 by root 2. So that will be n naught by 2 root 2. Let's take one more example. If let's say at time equals to 0, you have got n naught number of active nuclei. And at time equals to 4 years, in 4-year time frame, the number of active nuclei has changed from n naught and became n naught by root 12. Then at time equals to 8 year, can you tell me how many will be the number of active nuclei remaining? You will say, yes, sir, in 4-year time frame, the number of active nuclei become 1 by root 12 times. So starting from here, in the next 4-year time frame, the number of active nuclei will become 1 by root 12 times n naught by root 12, and that will gives you n naught by 12. If they ask you at time equals to 12 year from the beginning, how many number of active nuclei you will have? You will say, sir, in every 4-year time frame, the number of active nuclei become 1 by root 12 times. So from time equals to 8 year till time equals to 12 year, in this 4-year time frame, the number of active nuclei will again become 1 by root 12 times of from where you begin. So the number of active nuclei at time equals to 12 year will be n naught by 12 root 12. This is the basic idea, and I hope with this many examples you must have understood. It's a pattern, and it's a simple pattern. N naught 0.9 n naught 0.9 into 0.9 n naught 3 n naught by 4 3 n naught by 4 into 3 by 4 n naught by 6 n naught by 6 into 1 by 6 n naught to n naught by 3 to n naught by 3 into 2 by 3 again into 2 by 3 n naught by root 2 again multiply it with 1 by root 2 again multiply it with 1 by root 2. So that's the basic pattern. So this tells us equal percentage change in equal interval of time or equal fractional change in equal interval of time. So let's now talk ahead and talk about something called activity. Activity tells us the number of disintegration taking place per second. So if there are 20 disintegration taking place per second, you say that the activity of this sample is 20. Now beta, do remember that activity is nothing but minus dN by dt. Why minus sign? dN by dt itself is a negative quantity when you are talking about radioactive decay, because the number of active nuclei are decreasing. We place one more minus sign to make this whole term positive, and the activity is minus dN by dt. And since we know that dN by dt equals to minus lambda n, I can say that minus dN by dt is nothing but lambda n. So activity is nothing but lambda times the number of active nuclei. Activity is nothing but lambda times the number of active nuclei. Now bachcho, we know that the number of active nuclei at any time t will be equals to initial number of active nuclei into e raised to power of minus lambda t, which we got after integrating dN by dt equals to minus lambda n. So since the number of active nuclei at any time t is n naught e raised to power of minus lambda t, and you can call this quantity lambda n naught as the activity at time equals to 0. At time equals to 0, the number of active nuclei is n naught. So you can call this whole term lambda n naught as the initial activity. So you can say that the activity at any time t equals to initial activity into e raised to power of minus lambda t. So what is a naught? A naught is activity at time equals to 0, that is the initial activity, and A is the activity at any time t. So we can say that the activity at any time t equals to initial activity into e raised to power of minus lambda t, and easy to remember. The number of active nuclei at any time t equals to initial number of active nuclei into e raised to power of minus lambda t. Multiply both the sides with lambda, so you get lambda n, the activity at any time t, equals to lambda n naught, the initial activity, into e raised to power of minus lambda t. And what is activity? It is the number of disintegrations per second. Now we need to remember some units. There is something called 1 becquerel. 1 becquerel is the SI unit of activity. 1 becquerel means 1 disintegration per second. Then we need to understand another unit, that is 1 Rutherford. 1 Rutherford is 10 raised to power of 6 disintegration per second. We Indians find it difficult to remember it, but for Americans it's easy. 1 Rutherford is nothing but 1 million disintegration per second. 1 million is 10 raised to the power of 6, and that's why they chose this unit. So 1 Rutherford is 1 million disintegration per second, or 10 raised to the power of 6 disintegration per second. Then we need to remember one more type of unit which is important, that is what is 1 Curie. 1 Curie is also unit of activity. 1 Curie is 3.7 into 10 raised to the power of 10 disintegration per second. How to remember it? I mugged it up. First I mugged up 3.7, and once I remembered 3.7, 3 plus 7 is 10, so 3.7 into 10 raised to the power of 10 disintegration per second. 1 Curie is the activity of 1 gram of radioactive radium. Now this is easy to remember, as Madame Curie was the one who worked with radium. So 1 Curie is the activity of 1 gram of radioactive radium. So if you take 1 gram of radioactive radium, then the number of disintegration taking place per second is 3.7 into 10 raised to the power of 10 disintegrations. Now let's move on and talk about something called half-life. Half-life, the time in which the number of radioactive nuclei becomes half, that's half-life. So time interval in which the mass of a radioactive substance or the number of radioactive nuclides reduced to half its initial value is called half-life of the substance. Do understand that if you have got a radioactive substance closed in a container, isolated container, then the mass of container won't decrease. What I am saying here is mass of the radioactive substance decreases. It converts into something else. If you take radioactive radium, let's say, then after one half-life, the mass of radium present will be half, but the mass of the box will remain the same, more or less same. So if we think of half-life in terms of graph, we have already learned that the graph of number of active nuclei versus time goes something like this. Now half-life is the time in which the number of active nuclei becomes half. So if you have got this graph and the half-life of the sample is t, then the number of active nuclei will reduce from n0 and become n0 by 2 in a time equals to t. In another time frame t, the number of active nuclei will become half of n0 by 2, hence n0 by 4. In another time frame t, the number of active nuclei will become half of n0 by 4 and become equals to n0 by 8. So in each half-life, the number of active nuclei becomes half independent of where you begin with. So how to find the value of t half? It's easy. We know that at time equals to half-life, the number of active nuclei is nothing but initial number of active nuclei divided by 2. We can say that t equals to t half when the number of active nuclei becomes equal to initial number of active nuclei divided by 2, right? Now from the equation we know n equals to n0 e raised to the power of minus lambda t. We know that time equals to t half is the time when the number of active nuclei becomes n0 by 2. Substituting, we can say that n0 by 2 equals to n0 e raised to the power of minus lambda into t half. Cancelling out n0, n0, we can say half equals to e raised to power of minus lambda t half. Or you can take log both the sides. So you can say ln half equals to minus lambda t half. You can think of this half as 2 raised to the power of minus 1. So you get minus ln2 equals to minus lambda times t half. Cancel out minus minus, so you get t half equals to nothing but ln2 by lambda. So solving this particular equation, you get t half equals to ln2 by lambda, log of 2 to the base e upon lambda. And log of 2 to the base e has a value equals to 0.693. For the calculation purpose, I never use 0.693, I take it like 0.7. You have 693 or 7, it's one and the same thing. So we take t half equals to ln2 by lambda or 0.693 by lambda, and you need to remember this particular formula. Now we are going to talk how the number of active nuclei changes with time. So let's think of time, the number of active nuclei, the probability of survival, and the probability of decay. Here I will like to talk a little bit about what is the meaning of probability of survival. Probability of survival means whatever the number of active nuclei you have right now upon original number of active nuclei. And probability of decay means how many number of nuclei have decayed, that will be original number of nuclei minus the one which survives upon the original number of active nuclei. So probability of survival means the number of active nuclei that you have still with you upon the total number of active nuclei you had initially. And probability of decay means the number of nuclei that have decayed, which is nothing but total minus surviving upon the initial number of active nuclei. So let's say at time equals to 0, you know that the number of active nuclei is n0, and right now out of all of them, all are active. So what is the probability of survival? So sir, probability of survival is number of active nuclei upon total number of nuclei you had initially. Right now at time equals to 0, none of the nuclei has decayed. So the total number of active nuclei that you have right now will be n0. So the probability of survival will be n0 by n0, and that will be 1. Now what will be the probability of decay? Sir, you are talking about time equals to 0. Nothing has decayed till now. If nothing has decayed, then the total number of decayed nuclei will be 0 upon total number of nuclei you had initially, that is n0. So the probability of decay is 0. Nothing has decayed till now. Do understand that the sum of probability of survival and probability of decay should be equal to 1. Now let's talk about time equals to t half. After one half-life, the number of active nuclei will become half. So the number of active nuclei you will have at time equals to t half will be n0 by 2. What will be the probability of survival? Half. Why? Because sir, out of the total initial number of active nuclei, now only half of there. So half have survived. So the probability of survival will be half. And half have decayed. So the probability of a particular nuclei to get decayed will be half. And see, their sum is still 1. At time equals to 2t half, how many number of active nuclei you will have? You will say, sir, the number of active nuclei after 2 half-life will be half of n0 by 2. That will be equal to n0 by 4. Since the number of active nuclei we have still with us is 1/4 of the original. So only 1/4 of the original has survived and 3/4 has decayed. So probability of survival of a particular nuclei will be 1/4 and the probability of decay will be 3/4. So at time equals to 2t half, the number of active nuclei will be n0 by 4. Probability of survival 1 by 4. Probability of decay will be 3/4. At time equals to 3t half, the number of active nuclei will be half of n0 by 4. That will be n0 by 8. Only 1/8 of initial has survived. So the probability of survival is 1 by 8. And 7/8 of initial has decayed. So the probability of decay has to be 7 by 8. Now let's talk about this guy, and this guy is important. What will be the number of active nuclei at 10t halves after 10 half cycle? So you will say after one half-life, the number of active nuclei is 1 upon 2 raised to power of 1 times n0. After 2 half-life, the number of active nuclei is 1 upon 2 raised to power of 2 n0. After 3 half-life, the number of active nuclei is 1 upon 2 raised to power of 3 n0. So after 10 half-life, the number of active nuclei will be 1 upon 2 raised to power of 10 into n0. 2 raised to power of 10 is 1024. And this can be approximated to 1000. So we say that after 10 half-life, the number of active nuclei will be N0 upon 1024. And that can be approximated to N0 by 1000. And that can be approximated to 0.001 N0. So we say at time equals to 10 T half, the number of active nuclei will be N0 upon 1024. So out of the initial N0, only N0 by 1024 has survived. So what is the probability of survival? 1 by 1024. And that can be approximated to 0.001. Now you need to understand that 0.001 is 0.1%. It means that 99.9% of the material has decayed and only nearly 0.1% of the material has survived. If the probability of survival after 10 half-life is 0.001, then the probability of decay has to be 1 minus 0.001. So that will give you 0.999. So after 10 half-life, remember this is important. This is asked many a time. Only 0.1% survives and 99.9% get decayed. If they give you general number, what happens after n half-life? So you will say that after n half-life, the number of active nuclei will be N0 upon 2 raised to power of n. If the number of active nuclei is N0 upon 2 raised to power of n, then the probability of survival out of the initial N0, now you only have N0 upon 2 raised to power of n. So the probability of survival is what survived upon what you had originally. So that will be N0 upon 2 raised to power of n divided by N0, and that gives you 1 upon 2 raised to power of n. You can simply plug in the value of n as 1, 2 or 3 to get the above results. Now what will be the probability of decay? So probability of survival plus probability of decay has to be 1. So if the probability of survival is 1 upon 2 raised to power of n, then the probability of decay has to be 1 minus 1 upon 2 raised to power of n. And that is the result. Now bachcho, moving on and talking more about half-life. So there is a useful relation that you should know. We know that after n half-life, the number of undecayed atom, the number of active nuclei that you have is equal to initial number of active nuclei upon 2 raised to power of n. This is what you have after n half-lives. If let's say the half-life is t half and they ask you how many number of active nuclei you have after a time t. For the sake of understanding, let's take a number. If they say that the half-life of this particular radioactive substance is 5 hours, and how much undecayed substance you will have after 30 hours. So you will say in 30 hours, how many half-lives will be completed? 6. So after 30 hours, the number of active nuclei will be initial number of active nuclei upon 2 raised to power of the number of half-lives completed. That will be 6. So you can say the number of active nuclei, the number of undecayed nuclei after a time t equals to N0 upon 2 raised to power of number of half-life completed. And the number of half-life completed is nothing but the time frame divided by the half-life. The time frame divided by the half-life. So you can even write the number of undecayed nuclei after a time t as N0 upon 2 raised to power of t upon t half. Because beta t upon t half represents the number of half-life completed. This is the important relationship that you should know. So now let's talk about the last topic we need to cover, and that is mean life. The symbol we use for mean life is tau. It is defined as the sum of lifespan of all radioactive atoms divided by the total number of radioactive atoms. Let's say in a sample you have got huge number of radioactive atoms. Let's say the first radioactive atom decays after 3 seconds. The second one decays after 4.8 seconds. The third one decays after 6 seconds. So what is the average lifespan of all these radioactive atoms? What is their mean lifespan? So how will you find it? So you will simply add up the lifespan of all of them and divide it with the number of radioactive atoms you had, right? Now this is the basic definition of mean life. It is defined as the sum of lifespan of all radioactive atoms divided by the total number of radioactive atoms you had. So we can say that tau, the mean life, equals to sum of lives of all radioactive atoms divided by the total number of radioactive atoms that you had. And when you calculate it using integration, then the mean lifespan comes out to be equals to 1 by lambda. Now bachon, here are few things that we should know about mean lifespan. We know from the basic equation that n equals to n naught e raised to the power of minus lambda t. In a time span equals to the mean life. That is, in a time span equals to 1 by lambda. How many number of active nuclei would have decayed and how many would have survived? So you will say that at time equals to 1 by lambda or at time equals to 1 mean life, the number of active nuclei remaining equals to n naught into e raised to the power of minus lambda into the time, and the time we are substituting is equal to the time of mean life, and that is equals to 1 by lambda. Now these two lambda get cancelled, so what you get is n naught e raised to the power of minus 1. That can also be written as n naught by e. So if we take the time equals to 1 mean life, then we say that the number of active nuclei we have is nothing but n naught e raised to the power of minus 1, that is n naught by e. Now once we know that the number of active nuclei after 1 mean life will be n naught by e, what will be its value? The value of e is nearly equals to 2.7. So when in place of e we substitute 2.7 and calculate the number of active nuclei, we get it to be equals to 0.37 n naught. Take out the calculator, do 1 upon 2.7, you will get a number equals to nearly equal to 0.37. So the number of active nuclei after 1 mean life is 0.37 n naught. Yes, sir. So if you started with n naught number of active nuclei, yes, and after a time span equals to 1 mean life, the number of active nuclei is 0.37. It means that out of the total, 0.37 survived and 1 minus 0.37, that is 0.63, decayed. So one can even think of it this way, that 37% of original, 37% of n naught survives after a time frame equals to 1 mean life. So that is, mean life is the time interval in which the number of undecayed atoms n becomes 1 by e times or 0.37 times or 37% of the original number of atoms. If after 1 mean life the number of active nuclei you have is n naught by e, then after 2 mean life the number of active nuclei you will have is n naught upon e square, 1 by e times of n naught by e. After 3 mean life the number of active nuclei you will have is n naught by e cube. After n mean lives the number of active nuclei you will have is n naught upon e raised to the power of n. Keep this in mind. So after every mean life the number of active nuclei becomes 1 by e times, that is same as 0.37 n naught, that is same as only 37% of the initial survives. Now beta, you need to understand one more thing. We know that T half, the half-life, equals to ln2 by lambda, and ln2 can be written as 0.693. So you can say that T half equals to 0.693 by lambda, and we know that 1 by lambda is equals to mean life. So here you can think of 1 by lambda as mean life and write the half-life equals to 0.693 times the mean life. Now I ask you a simple question. Which one is greater, mean life or half-life? So one can say that, sir, you have to multiply a number less than 1 with the mean life to get the half-life. It means that mean life has to be greater than half-life. Or There is one more way to understand this. After one half-life, 50% decays and 50% survives. After one mean life, 63% decays and 37% survives. It means that in a time frame equals to mean life, the percentage decay is more. So mean life has to be a bigger time frame. That's why more decay takes place in this time frame. Hence, we can say that mean life is greater than half-life. So that's all in this hour. See you guys in the next hour where we are going to talk about semiconductors. All the best. Keep preparing well. Bye bye. So that's all for now. See you guys in the next hour.